So similar to how we looked at the arithmetic sequences, now we're going to look at geometric sequences. And geometric sequence use a multiplying or dividing pattern, but it's really always multiplication because dividing is just the same as multiplying by a fraction. Dividing by 2 is the same as dividing by 1/2. So just like arithmetic is technically all adding, and if it's going down we say we're adding a negative, all geometric sequences are multiplication, and if it is getting smaller we're just multiplying by a fraction or something less than 1, but we can look at it as dividing. So let's look at the first one. I have 3, -15, 75, -3, 75. So a lot of people can look at it and say, well, I'm multiplying by -5. Like arithmetic though, there is a trick that if you take each term and divide it by the term that comes before it, you will also always get that common, and now because we're not subtracting but dividing, we call it a ratio because a ratio is just a division. So in this case our common ratio is -5. That's what we're multiplying by. A is still and always will be the first term, so in this case A is 3. The formula for geometric series is AR to the n minus 1. You want to be really careful that the n minus 1 stays in the exponent. But now I fill it in, so it's 3 times -5 to the n minus 1, and that is the formula. A lot of times geometric formulas are less work than arithmetic because there's no simplification. BEDMAS says exponents come before multiplication. Because I don't know what n is and I can't do this exponent, I can't do this multiplication. This is not equal to -15 to the n minus 1, so make sure you don't ever multiply those in. Our next one, and here's where it's getting smaller. So it is a division pattern, but in this case we are dividing by 4. So there's two ways to deal with the common ratio. You can use a decimal 0.25, or you can say it's 1/4. And again, if you take any term and divide it by the term that comes before it, you are going to get 1/4 when you reduce it into lowest terms, because 128 goes into itself once and it goes into 512 4 times. A is 512. So now our our general term, when I fill in A times R to the n minus 1, becomes 512 times 1/4 to the n minus 1. Now I prefer fractions over decimals, but this would be the same as 512 times 0.25 to the n minus 1. So if you prefer decimals, it is okay to work with those. Okay, now we have some x terms, and the exponents look a little weird here, but that's squared to the exponent 3 to the exponent 4. So if I'm looking at the common ratio, I can say, what am I multiplying by? I'm doubling the numbers, times 2 times 2 times 2, and I'm multiplying by x each time because the exponent is going up by 1. X times x is x squared times x is x cubed times x is x to the exponent 4, etc. If you didn't see that, you can always do a division. 4x squared divided by 2x. When I reduce that, 4 divided by 2 is 2. X squared divided by x is x. A is 2x, so now Tn is ARn minus 1, which is 2x times 2x to the n minus 1. Now here is the one exception. I've told you never simplify and never multiply those together. But this is a special case because those are the exact same. So it's like I have common bases. This is a 2x to the exponent 1, and this is a 2x to the exponent n minus 1. When you are multiplying like bases, you keep the base the same and add the exponents. So it'd be 1 plus n minus 1, which simplifies just to n. I would probably make that jump from there to there if I was doing this on my own, but I wanted you to see that I was taking the two exponents and adding them together. So now I have again, not just a sequence where I can see what A and R are explicitly. I have to figure them out. So I have T2 is 81 and T7 is 1/3. Again, like with arithmetic, there is a way to look at the numbers and play with them and figure out what the ratio is and then subsequently what the first term is. If you are able to do that, that's amazing. Just explain your work to me. I'm going to work from the formula because this is a method that always works and it gives you something to do if you look at it and don't know what to do. So it's the same method as the arithmetic, except now we're working with the geometric formula. So the answer is 81 when n is 2. So n minus 1 becomes 2 minus 1. So 81 is AR to the 1, and I'm not going to bother putting the 1 because no exponent is automatically 1. 1/3 is the answer when n is 7. And when you are doing your own work, I am okay if you skip right down to the 6 and right down to the 1 as you become more comfortable with the n minus 1. Again, I have two equations, two variables, a and r. I'm going to isolate. It doesn't matter which one I isolate for. I'm actually going to isolate for a here. So a is 81 divided by r, and I'm going to sub into the other equation. So 1/3 equals a, r to the 6. I'm used to just putting a big old blank there, so I get 81 over r. I am going to show some steps here. You could do this in a reduced way, but I want everyone to see the math that I'm doing. R to the 6 is really r to the exponent 6 over 1, because to multiply fractions I go across the top, 81 r to the 6, and across the bottom, r times 1, which is now going to reduce to 81 r to the 5. I'm going to bring the 81 into the bottom here. The 81 is on top on the right hand side and represents a multiplication. So if I want to change it to a division, it's going to go into the denominator or the dividing part on the other side. So that's why I did 3 times 81 on the bottom. So now r to the 5 is 1 over 243. So r is, and again I'm showing all my work, you wouldn't have to show all these steps, but the opposite of exponent, or to the 5, is the 5th root. So that's going to give me r equal to 1 over 3. The 5th root of 1 is 1, because 1 times 1 times 1 times 1 times 1 is 1. The 5th root of 243 is 3. 3, 9, 27, 81, 243. So now I have my r. I'm going to figure out my a by bringing that back over and substituting it over here. So I get 81 over or divided by 1/3. I don't like fractions over fractions, so instead of having this here, I'm going to write it as a divide. You divide fractions by flipping and multiplying. So 1/3 becomes 3 over 1. So my answer becomes 243. 81 times 3, and really I have 1 times 1 on the bottom, which I don't need. Again, it would seem like we're done the question because we've done a lot of work, but ultimately we're looking for a formula for the general term. Now that I know my a and my r, I can substitute a in and substitute my r to have my final term.
In example 2, we're given a sequence in which we can identify that a is 7 because that's the first term, r is -2 because that's what I'm multiplying by to get from term to term to term. And again, we want to know which ordinal or which n is associated with the term -229,376. Because this is geometric, I'm going to start with my formula. -229,376 is the answer. It's the term when a is 7, r is -2, and I'm not sure what what n is at this point. So I'm going to begin to solve this. Just like when we were filling in the formula, I cannot put that 7 and that negative 2 together. I have to actually bring the 7 to the other side and divide to get rid of it. So I do that division and I get negative 32,768 equals 2 to the n minus 1. Oh, sorry, negative 2 to the n minus 1. That means this number is a power of negative 2. I need to figure out how many negative 2's does it take to get negative 32,768. There's a couple ways to do this. You can just go negative 2 squared, then to the exponent 3 to the exponent 4. I'm a little bit too lazy for that, so I actually, in my calculator, just guess and check. So it's a pretty big number. I know it has to be odd because I need to get a negative answer. If this is an even exponent, all my negatives will pair up and my answer will be positive. So I'm going to try negative 2 to the exponent, and I'm going to try 7. Not nearly big enough. 7, negative 2 to the exponent 7 is only negative 128. So I'm going to bump it up a bit. I'm going to try exponent 11. So I'm going to try negative 2 to the exponent 11. Still not big enough. So if I do 11, that's only negative 2048. I'm actually getting closer, but not near enough. So I'm going to try 15 as an exponent. Negative 2 to the exponent 15. And there it is right there. So negative 2 to the exponent 15 is negative 32,768. So 15. Now what I have on either side is a common base that has to be equal. That means the exponents have to be equal as well. So 15 has to be the same as n minus 1, or n has to be 16. So there's 16 terms in this sequence above.